new section. In this section, we are going to investigate Riemann integrability of monotonic functions, monotonically increasing functions, decreasing functions, those things. And the main result here is this proposition. So let's see what the proposition is. So as usual, we have a function f from this closed interval a comma b into R. F is a real valued function whose domain is this closed interval, and of course a and b are real numbers and a is less than or equal to b. A can be equal to b. In that case, if it will just be integrable. It will be constant. So that's a degenerate case. But a may be less than b also. In that case, this interval is non-degenerate and the question of integrability of f is not trivial in that case. And f is a monotonic function. So it's either monotonically increasing or monotonically decreasing. Then f is Riemann integrable. Okay, so we are not saying anything about f being or not being continuous. F may be continuous, f may be discontinuous. If it is discontinuous, we also don't know how many points there will be in this domain where f will be discontinuous. So anything can happen when we think of continuity or lack thereof of f. But still, f will be Riemann integrable if f is monotonic. Now, you may think, because we have already completed the section on integrability of continuous functions, and there we have come across that result that any piecewise continuous function is Riemann integrable. You may think that maybe all monotonic functions actually belong to the class of piecewise continuous functions, but that's not true. Now let's recall, in fact, before the proof is presented of this proposition, there is a remark. So let's see this remark. In exercise, so we are going to recall an exercise from the 9th chapter where we mainly discussed continuous functions. So exercise 985, in that exercise we saw a function f. This f, however, has the entire set of real numbers as its domain. That is, strictly increasing. Okay, strictly monotonically increasing continuous at every irrational number and discontinuous at every rational number. So such an extreme function was in fact investigated, and actually we proved these things. The function was defined for us by the author, and we proved this thing that it is strictly increasing. It's continuous at every irrational number but is discontinuous at every rational number. Now this function, when you restrict this of course has the entire R as its domain. But if you restrict the function on an interval like this, which is non-degenerate, say 1, 2, can that restriction be piecewise continuous? Possibly, no. Let's think of why that is not possible. You think of the restriction of this function on, say, 1, 2. In order for the restriction to be piecewise continuous, this interval should have a partition so that the restriction of this restriction on those individual subintervals of the partition should be all continuous. That, however, is not possible. Why? Because we know that there are infinitely many rational numbers in this interval, and our function is discontinuous at every rational number. So you cannot really come up with a partition, no matter how many subintervals you choose, you won't be able to tackle those rational numbers, in the sense that if you are thinking of avoiding those rational numbers, it cannot be done. That's because a partition has only finitely many subintervals, finitely many elements in it. And if you want to avoid these points of discontinuity, those should lie at the boundaries of those subintervals. But that's not possible. Finitely many subintervals give you finitely many choices for the boundary points, but there are infinitely many rational numbers. So no matter how large a partition you choose of this, at least one, actually not at least one, all of the subintervals in that partition which are non-degenerate will have, all of them will have infinitely many rational numbers. So no chance of having such a subinterval in which if you restrict f, then it will become continuous. No. That is why this is an example of a monotonic function which is not piecewise continuous, and that's why we cannot apply whatever theory or whatever results we have already uncovered about continuous, piecewise continuous functions and their integrability to this situation, because there is such an example, and maybe there are others also. That's why it makes sense to again say something about this class of functions. Now let's see the proof. To put all these things simply, not all monotonic functions are piecewise continuous. That's why we have to do again find integrability or non-integrability of this new class of functions. Now the proposition tells us what is the hypothesis. The hypothesis is simply that this function is monotonic. That's all. Nothing else is given. Now, if we really want to talk about its integrability, we must first make sure that it is bounded, because we only define integrability for bounded functions. But before we do anything else though, let's just consider the degenerate case first, because it's also a case. So this is how I am going to start the proof. The claim is trivial if A is equal to B. So let A be less than B. Also, let's give the interval a name. Let's call it I. Alright, now it's a closed interval. So how do we make sure that f is bounded? F actually is bounded. You can show it here itself in 2 lines, but the author has recalled a previous exercise where we have already done this. So let's use that. By exercise 981, F is bounded. I said you can show it in two lines. Do you see how? See, f is either, being a monotonic function, f is either monotonically increasing or monotonically decreasing. And accordingly, if you choose any x from your I, although we have written this, but let me just show you how this can be done or how we did it here. Suppose f is monotonically increasing, then for any x belonging to I, what shall we have? X belonging to I means this. Now, since f is monotonically increasing, so we will have this. That means all the f values are bounded from below by f of a and from above by f of b. That's why f is bounded. If f is monotonically decreasing, the inequalities will change direction, but still they are bounded. In that case, f of a will be an upper bound for the f values and f of b will be a lower bound. That's just it. Okay, so f is bounded. But now we must decide which one of these two things we should impose on f. That is, whether f is increasing or decreasing. Actually, we have to do both, but the author has chosen to discuss only the increasing case. In fact, the way he phrases it, he says that let's assume without loss of generality that f is increasing. This language is a little problematic because the decreasing case, it has to also separately, you have to show it. You cannot just leave it like that. We will come back to it. So I am not going to use that language without loss of generality. I will simply write this. Assume that f is monotonically increasing. We will handle the decreasing case afterwards. Okay. So now what we are going to do, we will immediately consider a partition of our interval I. Our interval I now has positive length because a is less than b, the length is b minus a. No matter how small it is, it's a positive integer. Now what we do, we start this part by choosing any arbitrary positive integer. Let capital N be any positive integer. So the status of n here is that of a variable actually. It is your choice. It's not something that has been chosen carefully so that something is satisfied. No, it's not like that. It's any positive integer. Now, consider the following partition of I. What is this partition? The partition is this. The elements in this partition are being called I suffix j, where j satisfies these inequalities, and there is one extra element also. where we need to now say what these ij's are. I think I better write it there. Ij is this. It's a closed open interval, closed on the left boundary side and open on the right side. A plus b minus a divided by n times j, comma, a plus b minus a divided by n times j plus 1. Okay, so it's open on this side. Now let's just think about what it is. What type of interval is it? That we can already see. Does it make sense? Yes. I mean, what I mean by making sense is this number greater than this number? Yes, it is. Let's talk a little bit about this interval ij. Note that this number is just this number plus b minus a divided by n. And the condition that a is less than b tells us that b minus a is positive, and dividing that by a positive integer n, you again get a positive real number. Okay. Now if you subtract this from this, then you get the length of this interval. So that means the length of ij is this. But shall we get a partition? That also we should check. No. Let's put some values of j and see what we get. So the first value of j is 0. So when j is 0, this is what the interval looks like, a. So the left boundary point is a, and what is the right boundary point? A plus b minus a divided by n, open. So that's the first, if you are looking at it that way, if you start from the leftmost side of the original interval I, which is a, then this is the first subinterval. What will the second subinterval look like? That corresponds to j equal to 1. So the second interval will look like this. Times 1, so that's just that. And if j is 1, here we will have 2. Okay, so that's how it goes. That means if you start sweeping the entire interval from the left side, you start from a and you keep on sweeping, and you just before reaching this point, you stop. That's how far this interval goes. But the moment you reach this point, the next interval has started, and then you keep sweeping this and stop before reaching this right end point. So that way you go. Obviously, okay, and how far can you go like this? What will be the last ij, in minus 1? So let's see what in minus 1 is. In minus 1, so this is I0, this is I1, and now we are going to write in minus 1. So say someone is going like this and eventually reaches in minus 1. So it's going to look like this: a plus b minus a divided by n times n minus 1. But now an interesting thing happens. What will you get if you replace j with n minus 1? J plus 1 will then become n. That is, you will get this. After cancelling n and then after cancelling a and minus a, this will be b. But recall that the right side is open. So we don't really get the single point b in this entire process of sweeping the interval from the left side and going towards the right side. We don't reach b. Just before reaching b, we stop. That's why in order to really have a partition, we adjoin this single degenerate interval b, which is a single point. That's why we need this b. And do you see these brackets here? Because this should be a degenerate interval. So that's a singleton set, but we are including it in the partition. That's why we need that type of brackets. Okay, so now it's clear that this is really a partition of our interval I. Okay, now what shall we do with this partition? We are now going to recall a result from our integration theory. Recall first that the definition of upper and lower Riemann integrals, the way we have given those definitions, the definitions involve integrals of piecewise constant functions. So this is not the usual way of having these things. The usual way involves upper and lower Riemann sums. But later on, of course, we linked our upper and lower Riemann integral to upper and lower sums, and that came in this result, proposition 11.3.12. So what that result says is this. Let's just recall that result. That way we will better understand this. That result says this. Say f is a bounded function. Then the upper integral of f is the greatest lower bound of all the upper sums. That's one part of the result. And the lower integral of f is the least upper bound, supremum of all the lower sums. Okay, so P is a partition. For this particular partition, also there will exist an upper sum for our function f. Since this upper integral is the infimum of such upper sums, so it will be less than it, see, being infimum means what? Greatest lower bound. So it's after all a lower bound. So the upper integral will be less than or equal to that upper sum which corresponds to this partition. So let's just write that and see what we get. So that is our result 11, proposition 11.3.12 by the upper integral of f over I, of course, is less than or equal to the upper sum of f for this partition. And we are straight away going to write what that upper sum is. Obviously, you know what an upper sum is. You have to consider the supremum of the function values in every subinterval of your partition and multiply that by the length of the subinterval, and you take the sum of such products. So we have actually two types of subintervals in our partition. Most of them are those ij's, okay, I suffix j. But one subinterval is that degenerate subinterval consisting of only b. The term that this upper sum has corresponding to that degenerate partition actually is 0. Why? Because that will simply be f of b times the length of b. Length of b means length of that single point, which by definition is 0. So that doesn't contribute anything to this sum. So ultimately what we end up having is a sum where only terms corresponding to those ij's remain. So we are going to write that. This is this. X varies over ij times the length of ij, where j varies from 0 to n minus 1. This is essentially the upper sum of f for that partition. Now, what does it become? And this is where the fact that we have assumed f to be monotonically increasing will be used. How does ij look? See, this is our ij. A plus b minus a divided by n times j, comma, a plus b minus a divided by n times j plus 1 open. Open closed, it does not really matter in the end. Because f is monotonically increasing on this interval and on any other interval, its graph is going to look like this. So the maximum, well, I should not perhaps say the maximum, but the supremum of f in this interval is going to be attained at this rightmost point. That's because f is monotonically increasing. So that makes this situation very easy. So this quantity will be equal to summation j equal to 0 to n minus 1 f of this a plus b minus a divided by n times j plus 1 times the length of the interval. But we already figured out that all our intervals have this length, b minus a divided by n. So the length is constant. Alright, so we get this. The upper integral is less than or equal to this. Now, if you write a similar inequality for the lower integral and use that other half of this proposition, the lower integral being the supremum of all the lower sums will be instead greater than or equal to that particular lower sum which corresponds to this partition. So let's write the steps. Okay, no point skipping the steps, making things unnecessarily confusing. Similarly, the lower integral of f is greater than or equal to the lower sum. So this time instead of supremum we will have infimum. That's the only difference. Times length, still here also we will have length, and again actually there is a term corresponding to that degenerate interval consisting of only b in this sum, but that becomes 0 because the length of it is 0. Now this time however, what will be the, where will you get the infimum? Again, because the graph of the function is like this, the infimum will be obtained at the left tail point. So the difference we will now have between this and this is here. So it will be f of a plus b minus a over n times j, not j minus 1, I mean j plus 1, times b minus a divided by n, that is the length of ij. Now we are going to subtract the lower integral from the upper integral, and that will give us this inequality. So we already know from our previous integration theory, the things we saw about bounded functions, that the upper integral minus the lower integral is non-negative. That's what we already know. So it was upper integral. This is less than or equal to this, and minus of this, if you multiply on both sides by minus 1, the inequality will get reversed. So minus of this will be less than or equal to minus of this. That is, the entire thing will be less than or equal to times b minus a over n, j varies from 0 to n minus 1, minus this sum. F of a plus b minus a over n times j times b minus a over n. Now of course you can combine these two sums. They are finite sums, no problem of convergence and or those things. So after simplification, you are going to have something like this. Actually, to make matters even more simple, you can take this length outside because that's independent of j. By properties of finite sums, it comes outside. And here, you can combine the two sums, and the thing you are going to have is this, f of this b minus a over n times j plus 1 minus f of a plus b minus a times j over n. Now if you look at this, some things are so well arranged. Things are so nice that many terms will get cancelled. It's a telescopic series, finite of course, and you will be left ultimately with only 2 terms. So it's very easy to calculate this sum, and it's going to look like this: b minus a divided by n times. So the term that will survive from this type of terms is the one that you are going to get by putting j equal to n minus 1. And we have already seen what happens when you replace j with n minus 1 here. Let's quickly again see what happens. You will get n here, that n and this n vanish, and you are left with b minus a. A plus b minus a becomes b. And another term will survive from these minuses, namely the one that you get by putting j equal to 0. That's just a, f of a. So this is what you ultimately get. That means this difference of upper and lower Riemann integral is non-negative, and at the same time is this. Now because your function is monotonically increasing, so f of b is greater than or equal to f of a, because b is greater than a. Actually they may be equal. We are not saying f is strictly monotonically increasing, just monotonically increasing. So this difference is non-negative. It's greater than or equal to 0. This difference is positive, and n of course is positive. However, do you remember that n is our choice? We could have chosen n to be very large, like 100 million, billion, trillion. Any n you choose, you will get this inequality. Now in this inequality, whatever else we have, besides n, we have b minus a, f of b minus f of a, this thing, nothing else is changing. So all these things have to be true despite what we choose in place of n, and that is why this cannot be positive. Now we have used this many times in analysis, but we don't really go into the details of why then suddenly we say that okay, because n is arbitrary, so this has to be 0. It cannot be positive. Let's see what happens when we forcefully suppose that this is positive. You give it a name also, okay? Say you call it epsilon. Suppose epsilon is positive. That forces f of b minus f of a to also be positive, because if this is 0 and epsilon is positive, then there is a problem, because epsilon is less than or equal to this thing. So now all these things are positive. B minus a was already positive. So what are you getting? You are getting this then. This is something we have already shown. That means now we have this 0 less than epsilon less than this. That implies what? Because b minus a and f of b minus f of a are both positive, you can multiply both sides of the this inequality by the reciprocal of their product and obtain this. Okay. Now this ratio is positive, and this of course is also positive, because both of them are positive. You can take reciprocal. Now the inequality will get reversed. That is, you get this. It was less, now it will be greater. The reciprocal of 1 over n is n. This means that no matter what positive integer we choose in place of n, it has to be less than this fixed positive real number. Can this happen? No. But why? Because it contradicts the fact that the positive integers have no upper bound, or it contradicts the Archimedean property. That is why we cannot choose epsilon to be positive. Since instead of writing all these things, because we keep on using this logic every here and there, so we instead write since n is arbitrary. The purpose of writing this arbitrariness is that we are indicating that n can be as large as we want. So things will go wrong if we really take n to be very large. So since n is arbitrary, we must have i.e. the upper integral has to be equal to the lower integral. Hence f is Riemann integrable. Actually, the proof is not over, because we have only proved the case where f is monotonically increasing. What about the decreasing case? Now, let f be monotonically decreasing, then minus f is monotonically increasing. How? See, f is decreasing means what? That if you choose your x and y in your interval such that x is less than y, then f is decreasing means what? F of x will be greater than or equal to, it will get reversed. I mean, the direction will be the other way. This is what f being decreasing means. But now if you multiply both sides by minus 1, again the inequality will change direction. And that's how the decreasing nature of f gets turned into the increasing nature of minus f. But we have just now proved that minus f is integrable. So, by what we proved above, minus f is Riemann integrable. We, however, do not want minus f, we want f. Now recall a result that we proved when we were going through the properties of integral. If f is Riemann integrable and you multiply f by a constant, any real number, then that multiple will also be Riemann integrable. We can apply that here. And in place of c, we are now going to take minus 1. Hence, f, which is minus 1 times minus f, is also Riemann integrable. I don't remember the result number, whether it's a proposition or theorem, but you know which property I am talking about, so I can't write anything like by that theorem. So you go back to that part and see for yourself which one it is. Is also Riemann integrable. Now finally it's over, complete. There is a corollary to this where we replace our closed interval by any bounded interval, and there are a few other things that come after this. So we will discuss that in the next analysis video. So I'm going to stop things here itself, and tomorrow we have again, what do we have? We either have number theory or we can do our class 11 mathematics, where the last section of trigonometric functions is still there. Which one should I do? Let me do number theory tomorrow. Next week we will do class 11 mathematics. So with that, let's just end things here. See you tomorrow with number theory. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.